In this video, we're going to look at a few different examples of calculating the torque on an object, possibly with the object at rest, and sometimes where the object is going to be accelerating. So using the torque to find the angular acceleration. So in this first problem, we have a 4-meter long, 500 kilogram steel beam that's supported 1.2 meters from its right end. We want to calculate the gravitational torque about its support. So the first thing that we need to do is to calculate the weight. The weight of the object is 500 kilograms times 9.8. So that's 4,900 newtons. Now, the weight of the object is acting at its center of mass. It's a uniform steel beam, and so the center of mass is at the center of the beam. So it's 2 meters from either end, which that means that it is 0.8 meters from the pivot point, or the fulcrum. And so we're going to use that 0.8 meters to look at the torque. And the torque that's on this, since this point over here is the pivot point, this torque is going to cause it to try and rotate around counterclockwise. So the torque is counterclockwise, and usually we take counterclockwise to be the positive direction. So the torque is counterclockwise, so it's positive. And the torque is going to be the force, 4,900 newtons, times this distance between where the force is applied and the axis of rotation. Again, this force is perpendicular to that line, so we're just using the 0.8 meters. And so that gives a torque that's 3,920 Newton meters. In this next problem, we have the same beam, but now we want to keep it balanced. So in that last problem, that torque would have caused an angular acceleration. It would have caused it to rotate around its end. In fact, we could go through and we could calculate what that acceleration is. In this one, we want the beam to be balanced. And so to do that, I want to figure out what the mass needed to balance this object is. So if this is balanced, that means that the counterclockwise torque is equal to the clockwise torque. The counterclockwise torque we just calculated was 3,920 Newton meters. That was on the last slide. The clockwise torque is going to be this weight over here, m times 9.8. So that's my force. And I need to multiply that by the 1.2 meters, which again is the distance from where that force is applied to the fulcrum. And if you go through and you do that, and you solve for the mass, this gives you a mass of 333.33 kilograms. And again, just to look at this to see if this makes sense, the center of mass of the beam is closer to the fulcrum than this box is. So the mass of this box should be less than the mass of the beam. The closer something is to the axis of rotation, the bigger the force is going to be because you'll have a smaller distance if you're trying to balance out the torques. So if you have a large person and a small person, you're trying to balance them on a teeter-totter, you have the larger person go in closer to the center, so that way the smaller person out farther away from the center can produce a bigger torque because of its large distance, and the bigger person, he has a bigger weight, and so you need to have a smaller distance if you want those torques to end up equaling each other out. Okay, in this example problem, this was something that I talked about a little bit in class, but we have a 100,000 kilogram rocket and a 200,000 kilogram rocket that are docked at opposite ends of a motionless 90-meter long connecting tunnel. The tunnel is rigid, so that means that it's always rotating about its point. It's not bending at all in the middle, so those rockets are staying on opposite ends of each other. And its mass is much less than that of either rocket. So that means that I don't need to worry about any rotational inertia for the tunnel. It's not uncommon to have to include rotational inertia for the tunnel, but for this, it's basically massless, and so the rotational inertia is zero. The rockets start their engines simultaneously and fire in opposite directions, each generating 50,000 newtons of thrust. So because those forces are opposite each other, the net force is zero, and that means that the center of mass does not move. There's no acceleration of the center of mass. So since it was not moving initially, it stays at rest. So that means that the center of mass stays stationary, and all that happens is these rockets rotate around. And what we want to do is we want to figure out what the angular velocity is after 30 seconds. Well, one of the things that's important is understanding exactly what's happening. So with this rocket is rotating around in a circle around its center of mass, and this other rocket is also rotating around in a circle around its center of mass. Okay, so just so we can tell those two apart. So this is a common thing. If you have two things rotating around a point, if they're connected together and they're orbiting each other or rotating around a common point, they're going to rotate around their center of mass. If you have two planets that are tied together, or you have two stars that are rotating, orbiting each other, they're going to orbit their center of mass. In fact, even when we look at the Earth orbiting the Sun, the Earth and the Sun together orbit their center of mass. But because the mass of the Sun is so much larger than the mass of the Earth, the center of mass of the system is basically at the Sun. It's not quite at the center of the Sun, but it's going to be a little bit away from the center of the Sun. It's going to be, we don't really have to worry too much about that. We didn't include that. But if we had a planet the size of Jupiter that was much closer to the Sun, say at the distance of Mercury, you would notice that effect on the Sun. You would notice that the Sun is going to wobble around, and that's because the Sun doesn't stay stationary. It's the Sun and that large planet would rotate around the center of mass. So that's what we have happening here. We have the two rockets. They're orbiting their center of mass. The one rocket is twice as big as the other one, and so it's closer to the center of mass. So the first thing that we have to do is calculate the center of mass. So the equation for the position of the center of mass is m1 x1 plus m2 x2 over the total mass. And again, you would do that for however many pieces you had. And so what I'm going to do is I'm going to let x1 be 0. So this smaller rocket is at a position of 0. So I have 100,000 times 0 plus 200,000 kilograms times its position of 90 divided by the total mass of 300,000 kilograms. So this gives a position of the center of mass of 60 meters. So that means that this distance for rocket 1 is 60 meters. And this distance from the center of mass to rocket 2 is 30 meters. Okay. The next thing to do is to calculate the net torque. Both of those thrusts are causing a counterclockwise rotation. And so the net torque is going to be the torque due to the thrust on rocket 1, which is 50,000 newtons times 60 meters. Because again, rocket 1 is 60 meters from the point, from the axis of rotation, and the axis of rotation is at the center of mass. And the torque due to the thrust of the engine of rocket 2 is 50,000 newtons times 30 meters. And so that's going to give a net torque of 4.5 times 10 to the 6th Newton meters. So that's 4,500,000 Newton meters. So again, ultimately we're trying to find the angular velocity. So we had to calculate where the center of mass was, and the reason for that was because this is orbiting the center of mass, we need to figure out the torques. And to find the torque, you need to know how far the forces are being applied from the axis of rotation. And so if it's rotating around the center of mass, we need to know how far the forces are from the center of mass. So we needed to figure out where the center of mass was. Once we knew that, then with the forces and those distances, we were able to calculate the net torque. And then our next steps, we're going to find the angular acceleration, and then from the angular acceleration with kinematics, we'll be able to find the angular velocity. To get the angular acceleration, we first need to find the rotational inertia. So to find the rotational inertia, the rotational inertia of a point mass is mr squared. So the total rotational inertia is going to be the rotational inertia of the first rocket, which is m1 times r1 squared, plus the rotational inertia of the second rocket, which is m2 times r2 squared. Now, r1 and r2 are labeled in the drawing. R1 is 60 meters, R2 is 30 meters. So the R1s and R2s are the distance of those masses to the axis of rotation. So the rotational inertia of this is going to be 100,000 kilograms times 60 meters squared. So that's the rotational inertia of rocket 1. plus 200,000 kilograms times 30 meters squared. That's the rotational inertia of rocket 2. Again, if we needed to include the tunnel, we would just add the rotational inertia of the tunnel here. Um, we would treat the tunnel as a long, thin rod. A long, thin rod about its center of mass is 1/12 ml squared. This is not rotating around the center of the rod, though, so we would use the parallel axis theorem, and we could figure out what the rotational inertia of that rod is. But because the rod has zero mass, 1/12 of 0 times its length gives 0. So this total rotational inertia is 5.4 times 10 to the 8th kilogram meters squared. And now that we have that rotational inertia, we can calculate the angular acceleration. The angular acceleration equals the net torque divided by the rotational inertia. Again, we have net torque equals rotational inertia times angular acceleration. That's just like net force equals mass times the linear acceleration. So torque plays the role of force, rotational inertia plays the role of mass, angular acceleration plays the role of linear acceleration. So the angular acceleration is going to be 4.5 times 10 to the 6th Newton meters divided by 5.4 times 10 to the 8th kilogram meters squared, which gives an angular acceleration of 0.00833 radians per second squared. And then finally, to find the angular velocity after 30 seconds, we're going to use kinematics. This has a constant angular acceleration because those thrusts are constant, so the net torque is constant. So we have that the final angular velocity equals the initial angular velocity plus the angular acceleration times the time. So this final angular velocity equals the initial angular velocity of 0 plus the angular acceleration of 0.00833 times a time of 30 seconds. So when I do this, I calculate that the angular velocity is 0.25 radians per second. Now, just like when we did kinematics for linear motion, you have to make sure that the angular acceleration is constant if you want to use kinematics to find the angular velocity. For this one, the directions of the thrust are always perpendicular to the circle that it's moving in. So that means that the angular acceleration is staying constant. The net torque is staying constant. If we looked at that problem of the beam that was rotating about its pivot, as it would start to rotate, the force of gravity would still be acting straight down. And so the torque changes as it starts to move. And so that would not be something that you could use kinematics for because the angular acceleration is not staying constant. If you wanted to find the angular velocity, you wouldn't be finding the angular velocity at a certain time, most likely, but you might figure out what the angular velocity is when it reaches the lowest point, and that's something where you use conservation of energy. Again, that's just like when we had something that slid down a ramp, it was okay to use it was okay to use kinematics because the linear acceleration was constant. But when we started to have things on curved slides, we had to start looking at the idea of energy because even though the acceleration wasn't constant, we could use the ideas of conservation of energy to still find the speed at the bottom. Okay, so I want to return to that beam. So that 4-meter long, 500 kilogram steel beam is rotating around a hinge connected at its left end. So it's a different setup than we had before. It's still that same beam though. So we have this beam, but now there's a hinge that's connected at its left end. And initially it's held horizontally and it's released. And I want to find its angular acceleration right after being released. So first of all, we have to find the torque. And so the weight of this from previously is 4,900 newtons. The torque's not the same that we had in that other problem though, because that force is being applied 2 meters from the pivot. So the net torque is going to be clockwise, but this clockwise torque is going to be 4,900 newtons times 2 meters. So that's 9,800 newton meters. Now, the rotational inertia of this rod, you could just use the fact that in several problems we talked about the rotational inertia of a rod about its end, and we said that that was 1/3 ml squared. But maybe you don't remember that. So the way that we would do this is we would break this up into little pieces dm, and dm is going to be the total mass per length times the thickness dx. X is going to be my distance from that piece to the axis of rotation. And the rotational inertia is, again, before it was m1 r1 squared plus m2 r2 squared. Well, for this, we're going to add up an infinite number of pieces, so it's the integral of r squared dm. But to do this, this is the integral. The distance from that piece to the pivot point is x, so r is x. So we have the integral of x squared. And instead of writing this in terms of m, that's why I needed this relationship. So that way, if my variable is x, then my differential is going to be dx. So I need to have this m over L times dx. And I'm going to integrate this from x equals 0 to x equals L. So this gives me m over L times the integral of x squared is x cubed over 3, and I evaluate that from 0 to L. So this gives me m over L times L cubed over 3, and so that gives me 1/3 m L squared. So for this beam, that means that the rotational inertia is 1/3 times 500 kilograms times its length of 4 meters squared. So if we calculate that rotational inertia, we get a rotational inertia of 2,666.67 kilogram meters squared. And so the angular acceleration is going to be the net torque divided by the rotational inertia. So again, the net torque was 9,800 Newton meters. The rotational inertia is 2,666.67 kilogram meters squared. And so that gives me an initial angular acceleration of 3.675 radians per second squared. Now, I said that if we look at a problem like this, as this beam starts to swing down, the angular acceleration changes. Just to show that, let's say that this beam has swung down at an angle of 30 degrees. The weight of this beam is still 4,900 newtons. This distance is still 2 meters, but what we want is, this is an example where instead of breaking the force into components, which you definitely could do, you could figure out what the perpendicular component of that force is. But the way this is drawn, it's a little bit easier to go through and find the line of action. So the line of action is a line that passes through the force. It's the line along which the force is acting. And then we need that perpendicular distance from the pivot point to the line of action. And so that's going to be 2 times the cosine of 30 degrees. So this distance is only 1.732 meters. So now the net torque is going to be 4,900 newtons times 1.732 meters. So that gives a torque of 8,487.05 Newton meters. You can see that the torque is getting smaller. In fact, when this beam would be hanging completely vertically, the torque would be 0. So as this swings down, the torque gets smaller and smaller until it reaches 0. And so again, I could calculate the angular acceleration here. It would be 8487.05 divided by the rotational inertia hasn't changed. That's just based on the shape of the beam. And so it's still a third ml squared. And so it's still 2,666.67. And so the angular acceleration has decreased to 3.183 radians per second squared. Again, it's very common to go through and calculate the net torque and calculate the rotational inertia and then use that rotational inertia to figure out the angular acceleration. You just have to be careful when you're calculating your torques. You have to make sure that you include all of the forces that are acting. You need to think about where those forces are acting. You need to make sure that you're looking at either the component of the force that's perpendicular to the r vector. Again, the r vector points from the axis of rotation to where the force is being applied. Or you look at the perpendicular distance between the pivot point and the line of action. So either way, you're finding the perpendicular component of either r or f, and you're multiplying it times the other one. These problems just take some practice, but with a lot of practice, you can go through, and a common thing is these problems where you have beams that start to swing down at an angle. And in a separate video, we'll look at conservation of energy and go through and figure out how you would find the angular speed when it is swung down a certain distance.